As we saw in the previous video or videos, complex ion equilibrium systems tend to be heavily product favored with K values that may be 10 to the 8th or 10 to the 12th or 10 to the 20th or whatever. And that creates an interesting solubility system once we combine insoluble species with complex ions or Lewis bases and stuff. But we'll look at that in a different video. I just want to extend this from the first round of complex ion equilibrium systems and say, all right, rather than just calculating, like, given this concentration of copper nitrate, find the concentration of this complex ion, let's write out the stepwise formation and then go back and find the concentration of everything in the end, which becomes kind of tedious. And what I'll do is I'll do some pausing along the way to save us effort. So let's get a goal here. Our first goal is going to be to write the stepwise formation. And that's kind of tedious, but at least it's easy. The second step, we're going to be given some information, and we're going to find the KF for this. So find the formation, KF, given, I'll say K1, dot, dot, dot. So I'm going to have those values that I happen to have made up in a very convenient way. And then the third thing is what's actually going to take some effort, and that's going to be to find the concentration of all species at equilibrium. All right, and that is a non-trivial step, but there are some tricks we can do to make it go faster. So writing this stepwise formation, I'm going to write that out. I'm going to leave a little space, and we'll take care of that business, and then we'll go back and use that information. So we've got CuNH3 2+, and I gave it to us as CuNO3 2. So the first thing I want to note is that NO3 is a spectator, and we're just going to ignore it. So I'll rewrite that as some indication here. We've got NO3 2. And we don't care about that NO3. It's a spectator here. It would be soluble. It's just floating around to balance charge. So we have Cu2+, and that's what we're going to start with, is that Cu2+. I don't know what's going on upstairs, if you can hear that thumping. Cu2+, maybe the apocalypse. And we're going to add to it our complex ion, our Lewis base, our ligand, this ammonia NH3. It has an electron pair that it can donate, makes it a Lewis base. Right there. And our copper ion's positive charge attracts that. We now have this system where it's CuNH3 2+. And there's a K expression that goes along with this, and I'll go back and write the other ones in later, but for right now, let's just write that our K1 is going to be products over reactants to their coefficient powers. I've said that a million times. NH3 2+, first power, Cu2+, first power, NH3, first power. That is our K1 expression. I actually have a value that I made up in a rather convenient way for that. I'll go back and add it later. I'm going to leave a little bit of room right here, and I'll write the next step, CuNH3 2. So we're starting with this. And this is just like the stepwise polyprotic acid dissociations where it was take an H off, this goes here. Take an H off, this goes here. Now it's add an ammonia, this goes here. Add an ammonia, this goes here, until we end up right there. So we're going to add another NH3. And that'll give us the next step in our system, where we now have two ammonias, and it's still a 2+. So that's something worth noting. If we used a cyanide or a hydroxide or something, our charge would be changing as we go. But since this ammonia is a neutral species, we're going to keep that 2+ all the way through. All right, I'll go back and write this K2 step later just to save us some time. Again, made it, use it. Made it, use it. Add another ammonia. Now we have 3 of those ammonias, still a 2+. There's our K3. And we're not there yet. We need 4 of them. Sorry, this new pad here, the light's all wavy, and I screwed that up already twice. But again, we're just using what we made to start the next step until we get where we need to go. Again, it's like those polyprotic acid dissociations where it was just take one H off at a time until they're gone. This is a 3 here, still a 2+. Again, charge isn't changing because the ammonia is a neutral species. And now we've ended up NH3, 4, 2 plus. There's a K4 that goes along with this. There's our stepwise formation. We started with our copper ions and the ammonia, and we ended up with the copper ammonia complex. Now I'm going to go back and fill these in. You don't have to stare at me while I write them. It'll just take a second. Luckily, while I was writing those in, I noticed there was a 2 missing right here. Here's the other K expressions, products over reactants to their coefficient powers for each of those steps. I want to write in the overall step, the formation of this, and it's like a Hess's law type of idea, linear combinations, and we're just combining those and crossing out. So like this is an intermediate, this is an intermediate, this is an intermediate, so they all go away, and I'm left with this and 4 of these and 1 of these. So my overall reaction ends up being copper 2 plus with 4 ammonias, giving us that complex ion CuNH3, 4, 2 plus. All right, that's beautiful. And we've got a K for this. We'll call it KF. And using those, our next step, so there's our stepwise formation. There's the actual equation for the overall setup. And we need a KF. And when you have these terms, and this was true when we did Hess's law type of stuff, any linear combinations of these combine to change your K. Like if you need to flip this one, it's negative times K, and so on. So when we need to add these K's, we're actually going to multiply them. So add, multiply, 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 multiply. And that K1, K2, K3, K4. All right, and I said given those K values, so now I need to give you those values. And again, I made these up, but I made them up in such a way that it works farther on down the problem. K1, 1.7 times 10 to the second, all right? K2, 1.0, 10 to the third. K3, 2.0 times 10 to the third. And then K4, 2.0 times 10 to the fourth, all right? And they're not totally made up because I happen to know this number right here, this KF for real. But when we get it, it's just this times this times this times this, which happens to be 6.8 times 10 to the 12th. And we've accomplished 2 of our goals. Yeah? One of our goals was this stepwise formation, and we've got that right here. And another one of our goals was find K. And we did that. K sub F is that. And now we want to find the concentration of all species present at equilibrium. And we'll look at that maybe 1.5 or 2 different ways, but we'll make it work correctly, or at least easily, once, and then we'll see how it goes from there. And the basis of this, and I'm going to write it down, it's important enough, is this is a big number. So the first step you do in these complex ion problems is to say you're going to assume complete, the reaction goes to completion. So assume reaction to completion. So I'm going to do some cheater stoichiometry over here, and I'm really militant about how I set up stoichiometry problems, except at this point in the game where I don't have time. All right? So this is going to be stoichiometry, and it looks like ice, but it's not. We're starting out with 2 times 10 to the minus third copper ions. All right? So 2 times 10 to the minus third molar. We're starting out with 0.8 molar for the NH3, and that was given, and we don't have any of this yet. Okay, and it still sounds a lot like an ice problem, except for the fact that I'm doing stoichiometry, not ice. All right, in this next step, if this is going to completion, because this number is so big, it's heavily product favored, all of one of these things has to go away. So we'll just say like, oh, I need 4 times as much ammonia as copper. This is my limiting reactant. This is my excess reactant. All of this is going to get used up, right? So I'm going to lose it all. We're going to lose 4 times 2 times 10 to the minus third, because it's a 4-to-1 stoichiometry, and we're going to gain 2 times 10 to the minus third. And so this is going to give us our starting amounts, and those amounts are 0. I have none of this left because we used it up. 0.8 minus that ends up being 0.8, again, because that number is so small, and 2 times 10 to the minus third, all right? So we have assumed that the reaction went to completion, and now we're going to treat it as an equilibrium system, which means we can't have a zero. It's going to have to shift that way, all right? So we're going to assume the reaction goes to completion, and then we're going to calculate the equilibrium in reverse. And we have this number. We just calculated what Kf is. So let's write that and then start making some use of it. Our Kf is supposed to be our products over our reactants to their coefficient powers. In this case, CuNH3. That's 2 plus. Concentration of that. Cu2 plus. Ooh. And NH3 to the 4th power. And it equals that number right there. So I can draw an equal sign. And now we're going to have to do an actual ice problem. And we're going to start with these values right here. So we've turned this into an ice problem with 0 on this side now. So initial amounts, change in equilibrium. Now, I have to point out, like, I did stoichiometry with concentrations, and you can do that because they're in the same solution. This really becomes an important situation when we're doing buffer chemistry. But for right now, we did stoichiometry. We could use concentrations. That's the way it is. Now, we assume the stoichiometry went all the way. Now it's time to see what equilibrium does. Equilibrium is going to have to make something on that side. Zeros have to go away. Equilibrium will shift towards zeros. This is going to have to go up by 4x, whatever x is, and this is going to have to go down by x. So our final amounts are going to be x, 0.8, minus 4x. You could say the minus 4x, but it's really, really tiny. We can punch it in. But note to self, the 4x doesn't matter. And this is 2 times 10 to the minus third minus x. And I think a simple mathematical approximation, well, let's write out what we have here, and then we'll roll from there. The numerator, 2 times 10 to the minus third minus x over our x times 0.8 minus 4x to the 4th power. And I think it's safe to say this will simplify. This is a huge number. This is going to stay big, and it's not going to change much. So this could probably be simplified as 2 times 10 to the minus 3 over x times 0.8 to the 4th power. And that's 6.8 times 10 to the positive 12th from right there. We can get an x value for that. In fact, I happen to have that x value. It's not big, all right? It is 7.2 10 to the minus 16th. X equals 7.2 times 10 to the minus 16th. You did not have to do this approximation. You could have set it up in a calculator and used solver and it would have been fine, but this is easier to solve. This is a molarity, and this is a really tiny number. So it's safe to say that 0.8 minus x, minus 4x is going to stay 0.8, 2 times 10 to the minus third minus x is going to stay 2 times 10 to the minus third. This is an important number for us. That's our copper ion concentration in the end. And I'm going to pause right there. All right, I'm done pausing. The reason I wanted to pause is because this is one of our answers. We need to identify what our concentrations in the final solution of things are going to be. And those of you who've watched the polyprotic acid dissociation problems know that there's kind of like a shortcut you can do to spotting what's going to be in your final solution. And that is everything down the side and over. And the basis of that was that I'm not going to take this concentration of NH3 because I've got a later one. But I've got a later one, that's the last time I see it, so that's the number I'm going to need, right? And as opposed to copper 2 plus ions, which I never see again, so I need that number right there. Over here, copper with 1 ammonia, I see again, so this is a later number, this is the one I'm going to go with. So the last time I see those things, those are the numbers I actually need. And here I think is the pivotal point in these problems, and I wish I had some color that would jump out of the page at this. In fact, let's fake it a little bit. This is our x, right? I'll circle that in Sharpie, and that is right here, 7.2. That is our concentration of copper ions in this equilibrium system. 7.2, 10 to the minus 16. Okay, that is that number right there from that overall equilibrium system. This is going to be 0.8. In fact, it's going to be 0.8 every single time. So as we're looking what we're going to have in the final solution, I have that answer, I have that answer, and I actually have that answer. It's 2 times 10 to the minus third minus x. So I don't really... 2 times 10 to the minus third. And this is a molarity and a molarity and a molarity. I will highlight those in blue, I guess. This, and this, and this, and this, and this, and this all came from right there. That was the sound of that highlighter, which is brand new, going in the garbage. Thanks, Sharpie Corporation. All right, we got it. Let's make use of it now, and actually, this is not set up like an ICE problem. It's super quick, given the fact that if we find one of these at a time, then there's only one we don't know. So for instance, we could find this right now, given the fact that we know these two things, right? But we know these two things, and we can find this right here. And I'll set one of them up, and then maybe we'll play the fast forward game, and I'll write the rest when you're not looking. But right here, this should then end up, I don't know, I'll just call it like A, whatever A means, over some numbers I know, and those numbers are 7 times 10 to the minus 16th times 0.8, all right? And we find out that that A equals 9.8 times 10 to the minus 14th. And that is this number right here, 9.8 times 10 to the minus 14th molar. And guess where that goes? Oh, it goes right here, doesn't it? 9.8 times 10 to the minus 14th. So just like those polyprotic problems where it's like, hey, I've got stuff here, I'll figure out what's here, and that's what I use there. But it's the exact same basic setup. Let's keep going on this. I said I'd pause, but it doesn't take very long. I'll call this like B or something. And then over here we've got 9.8 times 10 to the minus 14th times 0.8. And that ends up giving us 7.8 10 to the minus 11 for our B. And those are molarities. So this is 7.8 times 10 to the minus 11th molar. All right. In fact, let's write that. 7.8 times 10 to the minus 11th. And these highlighted ones were a note to me in advance which ones we're going to need. So as we set this one up, I've got that, we'll just call it C, 7.8 times 10 to the minus 11th times 0.8. And the reason this 0.8 isn't changing is because you have a ton of it compared to everything else, right? Like this started out 0.002 and this started out 0.8. And one of the things we had talked about with complex ion situations is having significant excess of your Lewis base, your complexing agent. That's what allows these complex ions to form. All right, our C in this case ends up being 1.2 10 to the minus 7th, which we can write here. And then this is 1.2 times 10 to the minus 7th. And we have all the numbers that we're going to need at that point in time. You could solve this one if you wanted to get this number right here. It does end up the same. I double checked, so that's good to know. Or you could work your way all the way through to here and get this number. One of the strategies I've suggested in class is getting this number right here and knowing this number right here to get this to plug in here, to get this to plug in here, to get this to plug in here, to get this. But it's convenient also. Like you can either use this number to go back and get all the in-between numbers, or you can use this number to go back and get all the forward numbers. One of my students, Jack Raymond, had suggested that if I write this at the top of the page, then I can write these steps. This one would be at the bottom, then this one, then this one. And just do it in reverse. So either way, you end up doing the same math and it works out the same. Let's list what we have in our final solution, which I do not think is necessarily obvious, but we labeled things in such a way it's convenient. I've got to worry about copper ions, right? So this is at equilibrium. We have some copper ions, and we have some coppers with 1 ammonia. And I realized, like, I don't want to double down on brackets like you're supposed to with complex ions. I think everybody can handle that. Put some brackets on here, and then we'll have a little chat about what the numbers are doing and why it makes sense that they're doing them. First of all, the NH3 stays 0.8 because it's in significant excess, all right? So that's 0.8 molar NH3. The Cu2 plus we calculated from this equilibrium system is going to be 7.2 10 to the minus 16. And we also calculated from that equilibrium system that the copper ammonia complex is going to be 2 times 10 to the minus 3rd molar. And that just leaves these 3 things, which we happen to have calculated here, here, and here. That's 9.8 times 10 to the minus 14th molar, and 7.8 times 10 to the minus 11th molar, and 1.2 times 10 to the minus 7th molar. All right. Once again, how do we know what's in the final solution? Our aqueous products are our complex ion products, and whatever you started with. So again, the basic idea when you have these stepwise complex ion equilibrium systems, look at the overall process, assume it goes to completion because those K values are always huge, then use equilibrium to go back. So we've got this right here, and that's what we did right here and right here. And then use those numbers that you now have to fill in all the other ones. And you don't even have to do ice because you'll know 2 of these for every single step, and you just use it to get the 3rd step. So this doesn't really end up ice. This just ends up copper is stuck at this based on the equilibrium. NH3 is stuck at this because you have so much, so just calculate that. Then this is stuck as is because those are stuck where they are. This is still stuck where it was, and then we get that number. And then everything falls into place. So reaction goes to completion. Can't have a 0, so it shifts back that way. Plug in everything in between. And then you've got these numbers over here. And I can't be negligent. I went back real quick and wrote in all those labels. This right here is our answer to the 3rd part.